Good evening, everyone. Welcome to another instructional video. Tonight's topic will be about moment distribution. In particular, we'll look at frames that do exhibit Sidesway. My coding for that is YSW, which basically stands for Yes for Sidesway. It is the 4th of August, a Sunday evening, 2024. It's about 20 minutes after the hour of 8 p.m. here in Los Angeles, and it's a very, very hot day. Just a few minutes ago, I just checked, and the weather is still about in the upper 80s, like 88 degrees Fahrenheit. Tonight's problem is the one pictured here. You have an unequal-legged frame with a uniformly distributed load. I've pulled this from McCormac's book, the 4th edition, titled Structural Analysis Using Classical and Matrix Methods. It's also found in another book that he wrote with Nielson in their 1st edition, Structural Analysis Understanding Behavior. You'll notice that the E that they give us is constant throughout. It's 3600 KSI. And then you do have some differing area moments of inertia, 1500 inches to the fourth for this column, whereas this column, the shorter one, is only 1000 inches to the fourth. The girder is also 1500 inches to the fourth. The big idea in solving a problem like this is what I'm trying to show over here in my plan. So first of all, we're going to analyze this in parts, and the reason to do that is because if you were to go back to, for example, the slope deflection approach, over there the equations did involve a chord rotation term. If you're using Hibbler's book, and most people will just term it the Greek letter psi. And well, moment distribution ignored such a term, and as a result of that, you cannot just apply moment distribution. You have to do it in parts. And so the way we do this is to, first of all, restrain the frame, and that's what I mean by NSW. That means no sidesway. And the picture here is by introducing, let's say, a fictitious support over here. And then you need to compute the reactive force here due to that fictitious support, where this frame is obviously not going to be able to sway because of that support placed there. That's part one. And then in part two, you do allow the frame to sway. In other words, you remove the support. And in that picture, it would be so nice if we could just take that reactive force, R, and reverse it. But there is one complication that disallows us from doing that so easily. The complication is that we do not know how to apply moment distribution to analyze for a joint force like this R. So instead, what we do is we impose some deflection. I'm calling this with a double bar to distinguish the double bar coming from the frame that is able to sway. Okay, so you're going to use your fixed end moments, allow that to undergo some sway, let's call it double bar delta, okay, and then you do your moment distribution, from which you can get this double R force, okay, after you do some statical analysis. And then after you do all of that, then you have to get your correction factor, or your scale factor. I call that my scale factor S. S then becomes your R force from this frame divided by the double barred R that we get from this frame doing some statics. Then you multiply that with the end moments on your double M frame, and then you add that to your end moments from your frame that was disallowed from swaying. Okay, and then when you add those, you get your final end moments, which is what we're after. To kick a problem off like this, what you need to do is compute your distribution factors. Those are your DFs. And to do that, you need to get your stiffnesses. There are a couple ways you can do this. I went ahead and got my relative stiffnesses because E is a constant after all, so you can just find the ratio I over L. And I just used some algebra to come up with some numbers. Like, for example, I found the greatest common factor of my I, that's between 1500 and 1000, that's 500. And so the factor that would be used is 3. So 3 times 500 would give me back the 1500, and for the 1000, 2 times the 500 would give me back the 1000. And then for the lengths, we have 3 lengths, as you can see, 20 for this long column, 30 for this girder, and then we have 10 feet for the shorter column. And so if you get the least common multiple of those, it works out to being 60. So the factors there are 6, 3, and 2 respectively. And then what I did was I just took that ratio for my relative stiffness factors. Okay, so I over L for the AB, and it comes out to being 9 times K, where K is I over L, and so on and so forth. So you get 9K, 6K, 12K. If you don't like what I just explained, you can also plug and chug. And the way to do that is just take your 4EI over L, that's for the stiffness factor, the full stiffness factor. And you can just say 4 times E, IAB is 1500 inches to the fourth, LAB is 20 feet. And so you see that KAB is in the proportion of 300 times E. And so you get these values, and then however you like to do it, then you have to go in and compute your distribution factors. The one complication you may or may not know about is when you start at the bottom, you do have this fixed location at A, and so when you're computing the distribution factor there, it's going to be the KRAB over the KR going from this fixed location, I'm just calling it a wall, out to A, and then going from A to B. All right, well, going from the wall, it would require an infinite amount of moment to cause a rotation. So that's why I have this labeled as infinity. And so the bottom is completely eaten up by that infinity. And so you have something divided by infinity. Well, that's 0. So the distribution factors for those fixed locations A and D are 0. Then you go in and you find your other distribution factors like BA. So let me just walk us through that real fast. So it's going to be the relative stiffness for BA divided by the relative stiffness of BA plus BC. Okay? And so you get 9K over 9K plus 6K. That's 0.6, and so on and so forth. Okay? All right, so let's go ahead and start with the first one. The first one is where we introduce a fictitious support, and we're trying to come up with this R value, this reactive force. And so to do that, we need to get the fixed end moments. Now on the one that does not sway, you apply the actual loads. So we have that uniformly distributed load. That's producing some fixed end moments of the order WL squared over 12. And I'm taking, by the way, counterclockwise to be negative and clockwise to be positive. And so I get negative 300 kip feet on the left at joint B, and a positive 300 kip feet for the fixed end moment at the right for joint C. And you'll notice that I have those here in my moment distribution table. And I've headed this as my no sidesway moment analysis, okay? So here are the joints. I have 4 joints, A, B, C, and D. And then we have these members, A to B, and then B back to A, B to C, and C back to B, C to D, and then D back to C. There are my distribution factors listed. And the way you do this is you start with your fixed end moments, as I said. There are no fixed end moments in the columns, and the reason is that there are no interior loads in the columns, as you can see. The only thing that is taking up interior loading or span loading is this girder BC. And that's where we had those, the minus 300 and 300 from joint B to joint C, respectively. The next thing you want to do, and I've tried to encircle these representing joint B and encircle these representing joint C, is then you want to unlock joint B, and then you want to apply an opposite moment. So we have presently a counterclockwise 300 kip foot moment. So I'm going to impose a clockwise 300 kip foot moment. So that's a positive 300. And then I'm going to distribute that in accordance to these values. So 6/10 of 300 positive gives me that 180, as you can see. And I put it in red as a positive, so it really stands out. And then 4/10 of positive 300 is going to be that 120. And you do that all throughout. And then the next step, this is how I count my iterations. So my first iteration, I counted starting with the carryover factor. If you go back to slope deflection, you'll remember that when you went from the pin into the wall, there was a half factor. So that's exactly what I'm doing. I've unlocked this joint. It's a pin presently. Now I'm going to push it over to the wall. And to do that, I have to take half as much. All right, so I have 180, and half of that is 90. And then 0, obviously half of 0 is just 0. And then 120's half is 60, and minus 100's is minus 50, etc. And then I've encircled the joint imbalance of moments once again. And we go through this process one more time. So then I distribute. How do I distribute? I take that minus 50, I unlock the joint, I impose a positive 50, and I distribute in accordance to these factors. So 6/10 of a positive 50 is that 30. And 4/10 of that positive 50 is that 20, etc. And so you go through various iterations until you're reasonably satisfied with those joint moments being balanced. In other words, being awfully close to 0. And then finally, what you do is you go column by column and add up those values. So if I went in over here and I added 0 with 0 and 90, 0, 15, 0, 3, 0, a half, 0, a tenth, and a 0, that adds up to a positive 108.6. And as I mentioned earlier, clockwise is my sign convention for positive member moments, and so I have a clockwise 108.6 kip feet acting at joint A. Okay, and so on and so forth. And so you can go ahead and see how to get those other values by adding up each of these respective columns, the values in those columns. After you do that, you have to apply some knowledge of statics. So we take, let's say, member AB, and we apply these moments. So for example, at A, I have this clockwise 108.6, as you can see. At B, I have this clockwise 217.23 over bar kip feet. And this member has a length of 20 feet. And so I have these end moments that are going, as per the right-hand rule, into the plane of the page. I must have an out of the plane of the page moment. And in order to achieve that, if I sum moments about point B, I have to direct my AX no sidesway reactive force to the right. And then if you compute that using basic statics, you'll find that that value is about 16.29 kips going to the right. I do the same thing for member CD. And then after that, I take the entire frame with its original loading with these reactions, and then I'm able to find my reactive force using simple statics once again. And so you see that your R value is 20.94 kips going to the right. Then we go in by superposition and we look at the same frame except we remove the original loads, and now we're looking at this thing as it is able to sway. In other words, we don't have that fictitious support. And what we're doing is we're momentarily restraining these joints from rotation, but we are allowing these things to drift over. Okay. Now, there are different ways you can do this, and I'm just going to show this by assuming a delta drift, let's say a sway, to the left of 1 foot. Okay, that's just arbitrary. And then I'm going to compute my fixed end moments, which, as we mentioned, is of the order 6 EI delta over L squared. And if you do that, you're finding that over here you have 1500 kip feet. And let me mention also here that the way you impose this moment is important. In other words, you can see that the compression is happening on this fiber of the column, okay? Likewise, the compression is happening on this fiber. So the moment's arrow, if you like, has to be on that compressive side, okay? So in other words, why is that so significant? Because these are clockwise acting moments. And so that value that I computed is positive, okay? And now, why did I know that? Because I'm imposing an oppositely directed force, R double bar, from the one that I computed here. See, this one was going to the right. Now I'm imposing one going to the left. Okay. All right, so then once you do that, you get your fixed end moments, as I'm showing here. The one on the left has a value of a positive 562.5 kip feet. Then you go through the moment distribution table once more. Okay, so now I'm showing all these fixed end moments. So down here I have a 562.5 at A, that's this value. Up here at joint B, I have this 562.5, which is clockwise, so it's positive. In the girder, I obviously do not have any chord rotation, so those are zeros. And then for this shorter column, CD, I have the fixed end moments that I had mentioned earlier, okay? 1,500 apiece. Then you go through the whole process that I just explained a moment ago. I'll just quickly remind us how that went. So you have your fixed end moments. Now you're going to do your distributions as per these distribution factors. And I've encircled the imbalance that exists at joint B, for example. I've encircled the imbalance that exists at joint C, moments-wise. And so you have a negative 250 kip feet of imbalanced moment at joint B. You unlock joint B. You impose a positive 250. That's a clockwise acting one, incidentally. And then you distribute that 250 in accordance to these values. So 6/10 of 250 is going to give you that 150 positive. And 4/10 of that 250 positive is that 100, okay? And then you go through your iterations as we explained, then you add up the columns, and then you find these member end moments, okay? So at end A, you have clockwise acting 465.44 roughly kip feet, and so on and so forth. Then you go through your statics one more time. And notice that I'm double barring everything just to distinguish these values from the previous ones so we don't get confused. And so your double AX reaction is about 41.7 kips going off to the right. And your double DX reaction is about 156.5 kips going to the right. And then you look at the entire frame. Okay, notice that the actual loading from the original structure, this uniformly distributed load, is not being considered here. Remember that. That was considered for the No Sidesway case. And so you compute your double barred R value, and when you do, it's coming out to about 198 point, let's say, 17 kips going to the left. All right, the next step to kind of wrap this all up is you need to compute your scale factor or your correction factor. Okay, so we imposed a unit type of a delta back here. If you'll remember, it was 1 foot, and then from there we were able to get our fixed end moments. So now I need to scale up or down in accordance to correct for that assumed value. That was just some arbitrarily assumed value. Okay. So to correct for that, I compute my S factor or my scale factor or my correction factor, however you want to refer to it, as the ratio of the R that was done from the No Sidesway to that of the double barred R that we just showed. And if you do, you're finding that it's approximately, just a little over a tenth is the factor, okay? And then what you want to do is you want to add up your No Sidesway moments that we evaluated together with the Yes Sidesway moments that are arrived at by pre-multiplying that factor, the correction factor, into the double barred M values that we just found down here, okay? So if you do that, I'll just take one as an example. So at joint A, we had a 108.6, which came from this value right here, the 108.6, that's the MNSW analysis table, plus that factor, the S factor that we just computed, 0.1057, etc., multiplied by this value that came from the double M bar analysis. Okay, that was the frame that could sway. So you have 465.44, roughly speaking, multiplied by that factor, added to the other one that I just mentioned, and then that's going to give you your total final end moment at joint A. Okay, so that comes out to being a positive 157.8 kip feet, and it's positive, so it's acting in a clockwise fashion. Then you go ahead and add up you compute all of these, okay? So go ahead and calculate all of these final end moments, and as you can see, these are the values that we're getting. As a last step, what you can do is you can go back to statics, or I didn't show that here, but another way to do this is the final reactive force AX would be equal to obviously the the if you went back to this picture right here, AX no sidesway, that's 16.2916 over bar, plus that correction factor S times the double barred AX, okay, which is this value, 41.69. So there are two ways you can do this. You can do it the way I just explained, or you can use your idea of statics that we've talked about already. And then when you go ahead and solve for your AX, that's the final reactive force on the original frame, the one we're trying to analyze, it comes out to about 20.7 kips going to the right. The DX reactive force is about the same going to the left. And then to show you the final results of everything, here they are. Here's your AX force. Here's your DX force. Then you can apply simple statics now that you know these moments and those horizontal forces. You can go ahead and compute these AYs and the DY by simple statics as I'm showing over here. And one last thing, you can also determine how much the actual sway was. And it turns out that it is that value that correction factor 0.1057, as you can see by the calculation shown right over here. So I'm saying also the actual sway is delta, not a double bar delta, obviously, is equal to the correction factor times the double bar delta, okay? And that is in feet, we impose the 1 foot going to the left, and so you see that that's how much it's going to sway to the left. Or if you compute that in inches, in other words, in a foot there are 12 inches, so you have to take this value and multiply it by 12. You see that it's approximately a little over 1 1/4 of inches, okay, going off to the left. I hope this was helpful to you. I hope to also see you in a future video. Take care. Bye-bye.